Hi and welcome to Concept Based. I'm John Hepworth. This is another one for the Year 11 Advanced students. We're still in working with functions and we're in the section Absolute Value Functions. Now, I love this section because the questions that it produces are solved both graphically and algebraically. And if you've watched any of my other videos, I will always say to students, hey, can you draw something first to double check your algebra? Well, in these questions, you literally are asked to do that essentially. And so I like that because it at least teaches students that, hey, this is a way that you can confirm that your algebra is correct by doing something graphically. All right, so let's delve in and have a look at what this question is. Graph y equals 3 and y equals the absolute value of 2x minus 1 on the same number plane, and hence solve the absolute value of 2x minus 1 equals 3. So first of all, let's talk about absolute values. What is this thing? Well, we also spoke earlier in this working with functions about when you have a function that you have a square root of something. So I'm just going to put x in here for the moment. If it's written like that, then we're only talking about the positive part of the square root of x. Sure, if you had a question where we took the square root at some point like this, then your answer would have to be plus or minus 2. Obviously, we've learned that before. But if the question already comes in the second line where the square root's been taken already, then we define in the question whether we're talking about the positive, or the negative. And in this case, we just have a positive square root of x, so that's what we're talking about. But that's not everything that we're talking about. If we took the square root of x, we'd get root x, not absolute value of x. What we're doing is taking the square root of x squared. So if you have x squared, that means any number that you put in there, whether it be a positive number, say positive 2, or a negative number, say negative 2, when you square it, you get a positive number. And then when you take this positive square root of it, the positive square root of a positive number is always positive. And that's all the absolute value is doing. It's saying, hey, whatever comes out from inside this absolute value, when we bring it outside, it has to come out as positive because we're going to square it and square root it and only come away with the positive answer. So that's the definition, and that's in your syllabus, of course. So we're looking now at two different graphs, y equals 3 and y equals 2x minus 1. Now, y equals 3 is a very easy graph to draw because we just go at 3 and we draw a line across, and this is y equals 3. All right, now this other part, 2x minus 1. Now, when I'm graphing absolute values, what I do first of all is ignore that it's an absolute value. So I just look at what would the graph of 2x minus 1 look like. So obviously that's going to go through here at minus 1. It's going to have a gradient of 2, and we're going to go up like this and have 2x minus 1. Now we notice part of this line that I've drawn actually goes below the y-axis, below the x-axis. And when it goes below the x-axis here, it's negative. So therefore that can't happen because it comes out of the absolute value and becomes positive. So something is going to happen right here at this point. What I then do is I go and graph the negative version of what's in that absolute value. I go and graph not 2x minus 1, but negative 2x plus 1, the negative of all of it. So let's go and graph that. Well, that goes through at positive 1. And it has a gradient of 2. That's a terrible version of that. Like that. And you end up with two different lines, and those two different lines meet here at the x-axis. And so obviously for that one that I drew, the negative 2x plus 1, we have some negative version part of that down here, which because it's an absolute value, that can't exist. So whenever it becomes this negative part of it, that's going to be removed. So therefore, none of these lines exist down here. We don't want to lose the y-axis. And we are now just going to graph this part here, which is our absolute value. Now, by graphing it, what we then can identify is that that graph is equal to 3 at two different points here and here. Now, we could solve this graphically. We could work out, well, where do these 2 points intersect and have a solution? But what I'm going to do is actually go ahead and solve that algebraically, and then I'm going to look at my algebraic answer and make sure that it's in line with the graphical solution that I have to make sure that I haven't made some sort of numerical error in my algebraic solution. So here we have absolute value of 2x minus 1 equals 3. And to solve that, I go and do exactly what I said I did up the top there when I was graphing, but I do it algebraically. So I decide to do the positive version of solving this. So I do 2x minus 1 equals 3. So just the positive 2x minus 1 equals 3. And that's a nice easy solve. 2x equals 4, x equals 2. But I also go and solve the negative version of this. So remember, the negative version of this is what happens inside the absolute value, and then it gets absolute valued and it becomes positive. So if we get negative 2x not minus 1, plus 1, that's the negative of all of it, equals 3. And therefore we get minus 2x equals 2, and therefore x equals negative 1. Now look at our two answers, x equals 2 and x equals negative 1. Let's go back up to the graph. Where is this answer looking like it's at? Is 2 reasonable? Let's look at this answer down here. Is negative 1 reasonable? They are. So the algebra that we are doing is confirmed by the graph that we have. And so therefore we are very confident in our solution because we have both a graphical solution and an algebraic solution. Now the note that I want to put on the end of this one is a little bit different actually now. It's when I teach students this, I always say to them, be careful. Don't always assume it bounces at the x-axis because you can write a function slightly different. What if we did the function y equals absolute value of 2x minus 1, but then we subtracted 1? Is it possible for that to ever be negative? Well, of course it is. What if 0 comes out of this absolute value? Because if we substitute in a half, we could get that out. But then we minus 1 and it would equal negative 1. So it can happen when there's some sort of adding or subtracting on the side. What would that look like? It would look like our 2x minus 1 graph, except it's moved down by 1. So the bounce is actually happening down here. So just be careful not to assume that it always bounces at the x-axis. However, I've got another caveat on that. I'll read directly from your syllabus. Graph y equals absolute value ax plus b. So it looks like this in your syllabus. So in your syllabus, there is no plus c on the end. So at the moment, in this part of your functions section, you don't have that offset where it moves up and down. But later, when you look at graphical parts of functions and you move them up, down, left, right, and dilate them and so forth, that will come in. So what I want to make sure is that when you are learning these absolute values to start off with, and you see this bounce at the x-axis happen all the time, don't let that be ingrained because we can shift this function and move it around. It's not always going to be in that position. All right, hopefully you like the fact that it's solvable both ways, graphically and algebraically, and try and take this idea into all of the other sort of solutions that you do where you can graph anything and solve it graphically alongside of solving it algebraically to just make sure that your answers are definitely correct.